All right, we are about to dive into a 2009 physics paper that asks one of the most incredible questions you can imagine, and honestly, it sounds like it was ripped straight out of a sci-fi novel. But the answer is grounded in some very real, and let me tell you, very mind-bending physics. You know, traveling between the stars, it's the ultimate dream of exploration, isn't it? But it's also one of our biggest, most fundamental challenges. I mean, the distances are just so ridiculously vast, and the energy you'd need is so enormous that, with what we've got today, it's pretty much impossible.
So this paper we're looking at, from physicists Lewis Crane and Shawn Westmoreland, it throws a total curveball. They basically say, forget bigger rockets, forget more fuel. Nope, the key to reaching the stars, they argue, is to create and then harness an artificial, absolutely microscopic black hole.
Okay, but before we get into their wild solution, we really need to understand the problem. Why is interstellar travel so unbelievably hard? Well, Crane and Westmoreland identified what they call the Interstellar Wall. This wall is really two huge issues. First up, deep space is just flooded with nasty cosmic radiation. To keep a crew safe, you'd need a shield that weighs at least 400 tons. And then there's the fuel problem. Even with something powerful like a fusion drive, you'd need so much fuel that the fuel tank would outweigh the actual ship thousands of times over. It just doesn't work. So what else is there? I know, the go-to sci-fi answer is always antimatter, right? But the paper points out it's just a logistical nightmare. Making it is crazy inefficient, and storing it is basically like holding on to a bomb that could go off at any second. A black hole, though? It's naturally efficient. It holds itself together through gravity, and it is the energy source. It's not storing energy, it is the energy. It solves all three problems in one, well, very extreme package.
So how on earth can a black hole, the thing famous for sucking everything in, be a source of energy? Well, the answer comes from the legend himself, Stephen Hawking, who found this incredible loophole in the laws of physics.
And that loophole is called Hawking radiation. The theory basically says that because of some quantum weirdness right at the edge, black holes aren't actually black, they glow. They leak a steady stream of energy and particles back out into space, and over unimaginable amounts of time, they actually evaporate. They're basically a power source.
And here's the most critical, completely backwards part of the whole idea. The relationship between a black hole's size and its power is inverted. Get this, the smaller you make it, the hotter it gets and the more violently irradiates energy. A giant black hole, like the one at the center of our galaxy, radiates almost nothing, but a microscopic one, it could outshine a star.
So this got Crane and Westmoreland thinking, is there a Goldilocks black hole? One that's not too big, not too small, but just right to power a starship. And they didn't just wonder about it, they actually did the math. They set up 5 practical rules. First, its lifespan has to be long enough for the trip. It's got to be powerful enough to actually push a massive ship. The energy you need to make it in the first place has to be something we could conceivably create. And at the same time, it can't be so tiny that we couldn't even focus the energy beam to make it. And last, its mass should be in the same ballpark as the starship it's powering. And here you can see those trade-offs in action. A really tiny black hole, just 0.9 atometers across, that's way smaller than a proton, is insanely powerful, but it burns out in just 3.5 years. Not great for a trip to another star. A bigger one, at 6 atometers, lasts for over 1,000 years, but it's way less powerful. But right there, smack in the middle, they found it. A sweet spot. The math showed that a black hole with a radius somewhere between 1 and 6 attometers checks all the boxes. A theoretically perfect engine for a starship is, according to the laws of physics, actually possible. So let's just run through the specs for their perfect 100-year black hole. First, its radius is a mere 2.7 atometers. We are talking deep, deep into the subatomic realm here. And yet, even though it's microscopically small, its mass would be 1.8 million tons. That's about the same as a huge container ship, which was one of their key criteria. Its lifespan? Right around 100 years. That's perfect for a multi-generational mission or a really long trip to a nearby star system. And the power output? It's a staggering 17 petawatts. That's 17 quadrillion watts. To put that in perspective, that is thousands of times more than the entire energy consumption of all of humanity today. All of it coming from an object smaller than the nucleus of an atom. Okay, so the physics works. It's mind-blowing, but it checks out. The next question is, How in the world would you actually build something like this? The paper goes even further, outlining a 4-part technological toolkit a civilization would need to really master this kind of energy.
It all starts with a generator to make the black hole. Then you need a drive to use it like a rocket engine. You'd also want to build power plants for stationary energy, maybe on planets or in giant space stations. And the final, ultimate step? A self-driven generator that uses the power from one black hole to make more black holes. That's basically an infinite energy source.
And just so you have a sense of the scale here, this isn't something you build in a garage. The paper estimates that just to make that first black hole, the core part of the generator would need to have a mass of about 1 billion tons. We're talking about engineering on the scale of asteroids. The idea is this. You build a giant, perfectly spherical gamma-ray laser in orbit, you'd mine asteroids for the parts, and then charge it up with enormous solar panels. Then, you'd focus an unbelievable blast of energy onto a single point, crushing it so intensely that it collapses space-time itself and becomes a black hole.
Now, all of this sounds like it's in the far, far distant future for humanity, right? But the authors make one final, absolutely thrilling point. If this is one of the ultimate ways to harness power in the universe, what if somebody else is already doing it?
And this suggests a totally new way to search for extraterrestrial intelligence. Forget just listening for radio signals. The paper proposes that these black hole drives would be constantly humming with high-frequency gravitational waves. If we could build detectors that are sensitive to these specific nuclear frequencies, we wouldn't be listening for a message, we'd be listening for the engine noise of a galactic civilization.
And that leaves us with the ultimate question, doesn't it? The physics here says this isn't magic, it's just really, really advanced engineering. So if a sweet spot for a black hole starship engine really does exist in the fundamental laws of our universe, it really makes you wonder, who else has already figured it out?